Now we have seen something called as context-free grammars, and the languages which are generated by context-free grammars are also called as context-free languages. Okay. Now similar to regular languages, in order to accept a regular language we needed a finite automata, right? And here, in order to accept a context-free language, we need a machine which is similar to a finite automata, and it is called push-down automata. So one thing about push-down automata is it is nothing but a finite automata to which some memory element is added, and that memory element is stack. So if I add a stack to finite automata, then I am going to get push-down automata. Okay. So in order to define push-down automata will have all this: q, sigma, delta, q naught, z naught, f and tau. So let me write about each one of them one by one. So first one is q. Capital Q is finite set of states. Okay. So it is same as finite automata. And sigma is input symbol. This is also same as finite automata. Delta is transition function. Q naught is initial state. It is also, everything is same as finite automata. And now Z naught is a special symbol which is used to mark the bottom of the stack. So inside the stack, whenever we start, we want to mark the bottom of the stack. So we are going to use Z naught. And capital F is set of final states, which means if we might use final state to represent to find out whether a string is accepted by the push-down automata or not. So sometimes this set of final state could even be empty, which means without a final state also we could accept some of these strings. I'll show you how later. And tau is stack alphabet. Stack alphabet means what are the symbols that I allow to be present onto the top of the stack. So this is all about the theory. We shall see some practical questions and we will understand more about it. And before going to that, let me tell you two things. Push-down automata is again of two types. One is deterministic push-down automata and other is non-deterministic push-down automata, similar to finite automata. Finite automata was also two types, right? So one is deterministic finite automata and other was non-deterministic finite automata. Similarly, push-down automata is also of two types. One is deterministic PDA and other is non-deterministic PDA. Now, if you see deterministic push-down automata, the transition function will be like this. If you are in a state, one particular state, and if you see some input alphabet, or either you see input alphabet or you see epsilon, any one of them could be defined, both of them cannot be defined. Okay. Then, and if you see tau, which means one symbol from the top of the stack, it is like this. You have a finite automata and which is having input. So input is present here and then stack. Okay. Now finite automata is going to be present in some state q. Let us say present state is q. Then finite automata is going to look into the input, and therefore I am going to write like this. So it is going to look into some symbol input, which could be either sigma, or in case the entire input is over, then there will be epsilon. Either it will be looking at sigma, which means some symbol a, or it will be looking at epsilon, which means the entire string is over. Then it could look at the top of the stack. That is why I am writing tau. Therefore push-down automata is going to see what is the present state and what is the present input and what is the present top of the stack. Depending on these three, it will decide what to do. It could either decide about it should go to some state q, some other state, or in the same state, and then print something onto the top of the stack, push something onto the top of the stack. If this is the case, then it is called deterministic machine, which means if you are in some state and if you see some input and if you see the top of the stack, and if you decide to go to some state and then push something onto the top of the stack, which means you are going to only one state and you are pushing something which is very particular, right? Then this is called deterministic push-down automata. Then what is the non-deterministic push-down automata is, you will be in some state q and you will be seeing some input and there will be some top of the stack, which means in one state, on seeing some input and seeing the top of the stack, if you decide to be if you want to go to more than one state and then print more than one symbol and then push more than one symbol onto the top of the stack, then it is called non-determinism. Okay, so simple. If you are in one state and looking at some input symbol and looking at the top of the stack, if you are going to only one state, then it is deterministic. If you are going to more than one state and then pushing more than one thing, how can you push more than one thing onto the stack is you actually make copies of yourself. That is how. Okay, so I think instead of going with the definitions, I'll take lots of examples and I'll make these points clear. Okay, so I'll take examples now and I'll explain you. In order to explain this pushdown automata, I'll take an example and I'll make this very clear. Let us say we have a language a power n b power n such that n is greater than or equal to 1. This is the language which we want to accept. So how I will accept it is, if you observe this language, we have to do one thing. We have to see all a's first and count the a's, and then whenever you see a b, we have to match the b's against a's. That is how we could actually pass this. So what is required is, I'll just take an example. See this, if I have a b b, then initially on top of this stack there will be z0, I'll see a and z0. Then what are you supposed to do? Whenever you see a, push a and go to the next a, and whenever you see the next a, push a and go to the b. So whenever you see a b, instead of pushing a, you have to pop one a and see the next b and pop this a, and after that once you reach epsilon and if the top of the stack is z0, you could stop it. Okay, this is the procedure. As long as you see a's, keep on pushing a's, and as long as you see b's, you keep on popping a's, and finally if the input is over, how do you know that input is over? Because there will be epsilon and then there will be z0 on top of the stack. So whenever you see z0, epsilon and z0, you could stop. Okay, so how to implement it as a finite this pushdown automata is, see this. Now let us say I'll be in state q0. Initially I'll be in state q0, and in this state q0 I'll keep on pushing a's, right? So what will happen is, assume that this is the input a b b and this is the stack, and this stack is containing z0. Okay, now input is a and top of this stack is z0. So whenever you say that you are seeing input, which means a, so I am going to write like this. Initially you will be seeing a and top of the stack is z0. So whenever you are saying that top of the stack is z0, actually you are taking that symbol out of the stack and you are holding it with your hand, which means this z0 is no longer on top of the stack, it is outside and you are seeing it like this. That is the meaning of it. A is in the input and z0 is on the top of the stack. When you say z0 is on the top of the stack, you have actually removed it, right? And now I want to push a. So I want to push a, but then I have to push z0 also. The reason is it is now outside. So that is how we see the top of the stack. That is the what can I say? That is the rule they have been using it. Why they are using it is, it makes things simple. So whenever I say that top of the stack is z0, remember that it is no longer on top of the stack. I have removed it out and I am holding it in my hand. Therefore, if I have to push anything onto the top of the stack, you have to push that z0 first. That is why it is a z0. Okay. Now z0 will be on top of the stack. On top of it, a is pushed. And next thing is I am again seeing a, right? So if I see a, and what is on top of the stack? A. So whenever I say a is on top of the stack, actually a is now outside, isn't it? If a is in the input and a is on top of the stack, a was on top of the stack and now I just removed it out. Therefore you have to push a, two a's. One a is for this a whichever you are seeing, and the second a is for this a which you have brought it out, right? Now you push back this a first and then the second a. Done. Now whenever you see a b, then you have to keep on popping. So from this state, whenever I see a b and small a is on top of this stack, which means I am seeing B and small a is on top of this stack, which means a is no longer on top of this stack. You have removed it out, isn't it? Whenever I say that a is on top of this stack, a is on top of this stack, it means that I have taken it out and I am holding it in my hand. Now pop off a. Actually I have removed a, therefore don't replace anything. This move is actually popping. Remember this. This move is actually pushing. This move is actually popping. The reason is I am saying that I have seen small a on top of this stack. When I said that small a is on top of this stack, I have actually removed it from the top, right? So I know replace it with epsilon. Therefore there will be simply a. Now I'll go to the next state, Q1. Just understand this. Why don't I be in the same state Q0 and keep on popping B also? The reason is, if I be in the same state and if I keep on popping the B for every A, popping A for every B, then what happens is, after A, B will come, and after a B, again A will come, and I will still accept it. But if I do like this, it is nothing but I am remembering that I have seen a B, and after which no A is allowed in the language. So by having two states, it is simply separating out, saying that after seeing a B, I am not supposed to see a, right? And now I will be in state Q1, and in this state Q1, as long as I see B and small a is on the top of this stack, I'll keep on popping it, which means if I see next B and small a is on top of this stack, I'm not going to push anything. That is by epsilon, right? So finally what happens? Finally you are going to see epsilon, which means epsilon here, and then top of this stack is Z0. So whenever you see epsilon, it means that the entire string is over, which means the entire B's are over. And whenever you see epsilon comma Z0, it means B's are over as well as A's are over, which means number of A's and number of B's are equal. So in this state, if you see epsilon comma Z0, then you could leave Z0 as it is and you could accept it, QF, right? So that is how the push down automata is built. Just understand what we did. Initially, as long as you see A's, initially only A is allowed, isn't it? Why? Because if the top of the stack is Z0, it means it is the first symbol. I am only allowing A. So if I see a in the input and Z0 on the top of the stack, I am going to push A. And then there will be A on the top of the stack and A will be input, and I'll keep on pushing A's. Then if the B is in the input and small a is on top of the stack, I'm simply popping off A. Then as long as I see B's in the input and when there are A's in the top of the stack, I'll keep on popping them. Then finally the entire input will be over, that is by epsilon, and then Z0 will be on top of the stack. So leave it as Z0 and accept it. This is called state transition diagram of the PDA. So one other way to represent this PDA is using transition function. I'll just show you how the transition function works. If you understood this, see this. Now I'll be in state Q0. I was in state Q0, and then if I see a small a and Z0 is on top of this stack, then I'll be in the same state Q0 and I'll push A Z0. Okay. Then I'll be in state Q0, A is in the input and A is on top of the stack. Then I'll be in the same state Q0 and I'm going to push A. Okay. Then I'll be in state Q0 and B is in the input and small a is on top of this stack. What are we supposed to do? We are going to match, but we have to remember that we have seen a B. Therefore, I am going to state Q1, and now the input is going to be popped off. Therefore, Q1 comma epsilon. Then I'll be in state Q1. In this state, I'll get any number of B's and A's will be on top of this stack. Then I'll be in the same state Q1 and I'll keep on popping B's for every A's for every B. Finally what happens is, finally I'll be in state Q1 and I'll see the input epsilon, which means the entire input is over and Z0 is on bottom of the stack. Then I'm going to state QF and I'm going to leave it as Z0. Okay, So this is called the transition function. Either I could represent the PDA using this transition function, or I could represent PDA using this state transition diagram. So you can follow anything. In all my examples I am going to use this state transition diagram to represent the PDA. So it is up to you. You could follow anything. Either if you like this you can follow this, or if you like this you can follow this. Okay, so both are valid methods. Now one thing you should observe is I am going to accept this string whenever I reach the final state, isn't it? So one other way of accepting it is you need not use a final state, this transition. What you could do is whenever you see epsilon, which means if the input is over, and z0 is on top of the stack, which means the stack doesn't contain anything other than z0, then you can leave it as epsilon, which means if you want to accept a string, you could empty the stack. This is called acceptance by empty stack. Okay, this is called acceptance by final state. This is called acceptance by empty stack, and you could do anything of it, which means here I could have this move, or I could be in the same state Q1. See, if the input is over and z0 is on top of the stack, I could be in the same state Q1 and I could simply empty the stack. So anything is valid. So if I do this, this is called acceptance by final state. If I do this, this is called acceptance by empty stack. Therefore, push down automata acceptance can be of two types. One is acceptance by final state, and other is you need not have a final state at all. That method is called acceptance by empty stack. You can use any of them. Either you could use final state or empty stack in order to accept a string by push down automata. Both methods are valid. Whatever you like you can use it, and it is important to remember that either if I use this method or this method, both the push down automatas are equivalent in power. And one more thing is either deterministic or non-deterministic push down automata, both are equivalent in power. Keep that in mind. Okay, so this is all about push down automata, and then this is an example of deterministic push down automata, and I have shown you two ways in which you can accept it. Okay, we shall see more examples. Now let us say I want to accept set of all strings such that number of A's in W is equal to number of B's in W. It is nothing but you have to count all A's and then match them against all B's. So this problem is very much different from a power n, b power n such that n is greater than or equal to 1. This problem is different and this one is different. This one is different in the sense, in this problem you are going to get all A's, then only you are going to get all B's. But in this one there is no guarantee that you are going to get A's and then B's. So A and B can come in any order, which means in this one you could either get AB or AABB. Fine. So this is similar to this, but this one even you can get BBAA or BABA or ABAB, right? Therefore you cannot say that for all A's I'll push A's and for all B's I'll pop A's. So we cannot use only A's to pushing and popping. So instead of that you should use some other approach. So what will be the approach is, if I see A, initially I am going to push A, and if I see B, when top of the stack is A, then I am going to pop A, which means I am going to push the symbols if I don't have any chance of popping, and I am going to pop the symbols if I have the chance of popping. For example, in this one, let us say BA, whenever you see a B, you can push B onto the top of the stack, and if you see a, then you can pop off B, and if you see a B, push B, and if you see a, pop B. And in this string, if you are seeing a, then you push A, and if you are seeing a B, now there is a chance of popping, pop A. If you are seeing a, push A, and if you are seeing a B, pop A, right? So if I have something like this, A, B, B, A, then if you see a, push A, and if you see a B, pop A. If you see a B, if there is nothing on top of the stack, then push B, right? And if you see a, then pop B, which means whenever there is a chance of pushing, popping, we are going to pop, and if there is no way I could match, then I am going to push. So how to write the PDA is, you are in state Q0. So initially anything can come, like A can come or B can come, so you should be prepared for both of them. Therefore, if top of the stack, if the input is A and top of the stack is Z0, which means this is initial configuration, initially A is coming, then you are going to push A, okay, or initially if B comes and if top of the stack is Z0, you are going to push B, okay. So this is fine, this is as the same. Then what happens is, if A is on top of the stack, if A is in the input and A is on top of the stack, you cannot do anything, right? So you cannot match. So in that case, you save this extra A also onto the top of the stack, so that you can match these two A's later with B's. And if B is on top of the stack, and B is in input and B is on top of the stack, you cannot do anything, therefore let it be there, right? So initially A can come, you are going to save it, B can come, you are going to save it. So if A is on top of the stack and if you are getting one more A, you are going to save it for later popping. And if B is in input and B, you are going to get B on top of the stack, then also you are going to save B for later popping. Then if A is in the input and B is on top of the stack, this is a chance where you could match, then you are going to pop off. Or if A is in the input, if B is in the input and A is on top of the stack, this is the time when you are going to pop, okay. So A is in the input, B is on top of the stack, then there is a chance of matching, then you are going to match. Or B is in the input and A is on top of the stack, there is a chance of matching, then you are going to match. So finally what happens is, everything it will be over, which means input will be over and top of the stack will be Z0, and you leave it as Z0 itself and you accept it in the final state, okay. So I'll just take an example and explain you what has happened here. Let us say it is A, B, 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 A. If this is the input, what happens is, initially Z0 will be on top of the stack and you will be seeing at this A, you are going to push A, then when you see this B, you are going to pop A, and next when you see this B, you are going to push B, because stack is empty and you don't have anything to compare this B against, right? And next when you see B and B is on top of the stack, you are going to push B, and next when you see A and B is on top of the stack, you are going to pop it, and next when you see A and B is on top of the stack, you are going to pop it. When the entire input is over, it will be epsilon and Z0, which means epsilon and Z0, and you are going to accept it. So you need not use more than one state here to do all this. In the same state, you could do both pushing and popping. The reason is, A's, after A's, B's can come, and after B's, A's can come. So both are allowed. In the previous question, after B's, A's should not come. That is why I was going to a different state and then doing pushing and popping. Okay, we shall see one more example. So let's see the next one. A power n, B power n, C power m, such that n comma m is greater than or equal to 1. So if I want to construct a push down automata for this one, A power n, B power n, C power m. So first thing you should observe is, A's and B's have to be compared and they should be equal. Therefore, the logic is, for every A we are going to push A, and for every B we are going to pop A. And then if you see C's, we need not count them at all. It is nothing but, C power m, n is greater than or equal to 1 is nothing but C star. Just the push down, the finite automata is enough. We need not do anything with push down automata. So compare these two and then simply read C's, and there should be at least one C. That is important. So if you see one C, go to the final state, and then after that any number of C's, you be there. Okay. So let's see how to do this. First one is, you will be in initial state, and as long as you see A's, you keep on pushing A's onto the stack, which means you will be in initial state, and if top of the stack is Z0, you are going to push A, and if top of the stack is A, you are going to push A. So because of these two moves, the entire A power n will be pushed onto the stack, and then once you start seeing B's, then top of the stack could be a, then you are going to replace it with epsilon, which means we are simply popping b's. And then whenever you come across a b, again top of the stack will be a, simply replace it with epsilon, pop off completely b's. So by this time you are popping off this, then entire a's will be popped off by the time you reach this part, which means top of the stack will be z0 now. So if you see c in the input and z0 on the top of the stack, which means c is in the input and a's and b's are completely mashed out, then leave it as z0. I don't want to do anything with the stack because I need not count c's, directly go to final state. In this final state, if you see c and z0 is on top of the stack, leave it as z0 and you keep on accepting it. So using this we would accept a power n, b power n, c power m, right? So one thing you should observe is, actually I'm calling such diagrams as the deterministic push down automata. In the previous example also it was deterministic push down automata, and now also it is deterministic push down automata. But then you should get a doubt that in case of deterministic finite automata, for every state, for every input I was giving transition, right? But here for every state, for every configuration I am not giving transition, which means, see this, if the input is a, b, c, then a will be pushed, and for b a will be popped, and for c it will be accepted. If the input is bc, think about what happens. Top of the stack will be z0 and the input will be b, isn't it? Now you will be in this state q0 and you will be seeing b comma z0. For b comma z0 nothing is defined, that is called dead configuration. Whenever you come across any string which is not in the language, then you will come across dead configuration. Therefore for that dead configuration the push down automata will halt and say that it is not accepted. So in q0 itself it will halt. The reason is you are not defining it, right? Let us say you are in the given string is a, b, c, c, right? This string is not in the language. Let's see what happens. So initially you will be in state q0 and you will push first a and then second a, and on seeing b you will move to the state q1. Okay, you will move to the state q1 and you are going to pop off the first a. Then you are in state q1 and now you will see c, but you will see c and the configuration will be top of the stack will be small a, which means here it is c comma small a, but you are seeing c comma z0. So you are defining the transition only for c comma z0, but top of the stack is actually c comma a, which means you have one more a. Again this is dead configuration, therefore PDA will halt in the state q1. So whenever the input is present in the language, we are going to reach the final state. If the input is not in the sequence which we require, then the push down automata is going to come across something called dead configuration and it is going to halt there. Okay, so this is nothing but halting. So definitely it will stop in a non-final state and we can say that this string is not accepted. Either the string is inside the language or the string is not inside the language, we are definitely going to halt either in the final state or in the non-final state. Definitely we are going to halt. We are never going to go through infinite loops here. Okay, so we shall see one more example.